Hey, good morning, welcome to my YouTube video, and in this video I will continue to update my pseudocode of my workflow scheduling algorithm. And first, so this is a whole picture of the workflow scheduling algorithm. The whole idea is we need to uh, minimize the data transfer time as much as possible. So because our scenario is that we'll use data instant workflow, it means that sometimes the data transfer time is bigger than the communication time. So we want to minimize this kind of time. And this is the whole idea. And first we need to add the entry and exit and their edge dependency into workflow graph D. And also, since the entry and exit is just a symbol, and so their data transfer time and communication time is computation time is 0. And second, we mark the entry and exit nodes as passed. So because we'll use the critical path to pass all the graph. Then we compute the priority value for each task, and the priority value is we just use upward priority value, and which is coming from Swiss paper and Swiss formula. And then we compute the last finish time and earliest start time for each task, and and then we need to find all the critical paths in the graph D based on the priority value of each task and the workflow task dependency. And the sixth step is we combine the path which has single task with its dependence into some other critical paths. And the seventh is we assign all the paths to a feasible virtual machine. And let's go to the how to find all critical paths in graph G. And the input is the we can have all the priority value for each task, and then we select the first and past task which having the highest priority value. We mark the task as passed, and we do a deep first search until a successful which is passed already. And then after we finish this part, and we will select to know. So if the path size is equal to 1, so we add path to the 1 size path list, and also we can assign the last finish time for each task with the last task's last finish time in this path. And this step is finished, then we can go to the path combination. So what's the path combination? It means that we want to just for some tasks which is only one critical path, which is only one task, and we want to combine this task into the current critical path. And then so we start from all the tasks in the one size path list, and then we select the first one. We find the critical path whose element has some data movement with the current task. So we will mark the critical path as P. So if the current task children is in P, so we add the current task directly before the children task of P and update the P. And also we have a different scenario, which is the current task's parent is in P, so we add the current task directly after the parent task of the P, and we update the P. So here we also need to update the so at last we need to go to the path assignment part, and all the critical paths which is already assigned the LFT and the EST, and we make the decreasing order of all the passes based on the each last finish time, and we start from the first pass of all the pass list, and we send the whole pass into the cheapest virtual machine instance. Then we update all the pass tasks children earliest time and all the tasks parents last finish time. Then we can update all the remaining paths last finish time, and we will repeat until we reach the last pass. So this is the whole picture. So right now this graph is not very suitable to the algorithm. Yeah, this example is not very suitable to the algorithm. I will concrete another example to show the efficient and do a comparison with the IC PCP algorithm. So this is the whole idea. Thank you for watching.